Welcome back. We are going to start the second part of the first set of slides. This is still in chapter 3, and we are going to go a little bit into depth on the grammars a little bit, and then we will switch to the semantics topic. All right. Okay. Yeah, we have seen context-free grammars in the previous set of videos, okay? And that's a very precise and a relatively easy mechanism to describe the syntax of programming languages. And if you recall, the definition of a grammar was it contains a set of symbols. Some of them are non-terminal symbols representing higher-level abstractions of the programming constructs, and the terminal symbols, which are the tokens, which correspond to the tokens of the language. And one of the non-terminals is designated the start symbol, okay? And that's where all the derivations begin, okay? And of course, the main part of the grammar is the set of grammar rules, or production rules as they're called. And these grammar rules, there is a few shown here. They on the slide, for example, they consist of a left-hand side and a right-hand side, okay, separated by this colon or sometimes an arrow, okay. And the left-hand side must be a non-terminal, a single non-terminal, and the right-hand side could be a combination of terminals and non-terminals, okay. And the way these grammar rules were used is in the derivation. You start with the start symbol, and that start symbol string becomes the current working string, or referred to as the sentential form, okay. And in the sentential form, you look for a non-terminal to expand. All right. If there's no non-terminal, then we are done. We have reached the end of the derivation. But if there is a non-terminal, or if there are more than one non-terminal, you have to choose one of them. And there are two standard ways to choose them. One is the leftmost, and the other one is the rightmost. And once you've chosen the non-terminal to expand, then you go scan through the rules of the grammar and see which of the rules define this non-terminal. That is, which of the rules contain this non-terminal on the left side. And you may again have more than one choice. Hopefully, you will find a rule. Otherwise, that's problematic. That is, you introduced a non-terminal on the right-hand side, but never gave its definition on the left-hand side. That's a problem, okay? And that's not a good grammar to write. So hopefully you'll find at least one rule for this non-terminal to expand. And of course, if you had more than one rule, you have to intelligently pick the right one so that you can make progress towards the final step, okay? And once you find the rule, you replace the non-terminal in the sentential form by the right-hand side of the rule, okay? That's all. So erase the non-terminal from the sentential form, and in that same spot, replace or introduce the right-hand side of the rule, okay? And then keep doing this process on and on and on and on, okay? So that's the how the grammar rules are used, okay? Now, in the next few slides, we're going to look at some subtle points of grammars in general, okay? And we have to be careful. These have important implications. The first topic is ambiguity, okay? And this comes up quite a bit with expressions, arithmetic expressions, but even other like if then else, nested if then else, and so on. So there are some constructs in programming, which syntactic constructs, which if you're not careful, you may design a grammar which makes the meaning of those constructs ambiguous. Okay, that is, you may mean one thing, or the programmer who wrote the code might mean one thing, but the compiler understands it as something else. Okay, so and that would be a problem, right? So ambiguity. So let's look at what this concept of ambiguity is. Okay. Here's a definition. We define a grammar to be ambiguous. Of course, there's another definition, a more general definition of a language being ambiguous. Okay, we won't get into that topic in this class. it's a topic discussed in the automata formal languages class. Okay, but right now we are focusing only on the grammar being ambiguous. Okay. The other concept is the language, the whole programming language being ambiguous. Okay, not referring to a particular grammar for that language. Okay. All right, that's a more difficult concept. Okay, and we will skip over that. But here we do want to define a grammar that is ambiguous. Okay, and the definition is that if the grammar generates a sentence or a string, sentence is the word used for the terminal string at the end. Okay, basically the whole program which you write or an expression you write. Okay, sentence, that's called a sentence. Okay, a grammar that generates a sentence for which there are two or more distinct parse trees. Okay, then it is ambiguous. Okay, so not for every sentence, but at least one sentence is there. Okay, so that's what this one says. Oh, so you have to be careful with these small keywords. Okay, a grammar that generates a sentence. Okay, means at least one. Okay, there's at least one sentence or a string you can name or you can write, such that there are two or more distinct parse trees for that. Okay, so let's look at some examples for that. Okay, the first one, I believe we'll have at least two examples here, but the first one is the very traditional arithmetic expression example. Okay, and this is something we have dealt with maybe even in grade school. Okay, when you learned plus and minus and multiply and divide. Okay, if you look at this expression in red here, a equals, this is an assignment statement, but on the right hand side of the assignment statement is an expression, arithmetic expression, b plus c times a. Okay, and if you were not familiar with the rules of precedence, okay, then there are two ways to interpret this sentence, right? One is to add b and c first, and then the result you multiply by a. And the other one is to multiply c and a first, and then the result you add to b. Okay, and obviously you all know that these two interpretations will probably give two different answers to that expression, right? And that's has been resolved in grade school and middle school or wherever this was taught by rules of precedence. Okay, there's something called PEMDAS or something like that. Anyway, there's some acronym to remember to tell which one is higher precedence and which is lower. And usually it's the multiplication gets precedence over the addition. Okay, but that's all for the human being. But if you write a grammar and if you code it into a system, the compiler may have some issues with that, especially if it cannot understand which one you meant. Okay, so let's take the grammar given here on the left side here. This is a grammar we have seen before. Okay, it's one of those I think one of the examples we have used in the past. Okay, and we have three IDs, A, B, and C. That's it. Okay, and an expression. Of course, the assignment statement is ID equals expression. Okay, so the first line tells you that's how you write an assignment statement. Our focus is more on the expression. Okay, assign, of course, is the start symbol, and then expressions. There are four types of expressions. Okay, the last two are just the parenthesis and just an ID by itself is an expression. Okay, and the second and the third are the ones which describe the plus and the times. Okay, we are just looking at the two operators and not other operators at this point. Okay, so just the plus and the multiply. Okay. Now you can see that it's very symmetric definition here, right? This is pretty symmetric. These two rules look the same except for the operator, right? Expression plus expression or expression times expression. Okay. So that the symmetry should give you a clue that this can lead to ambiguity. Okay, because it's so symmetric, you could choose either of the two rules and then break that b plus c times a into two different ways. Okay, and that's the reason why this particular grammar is ambiguous. Okay, and let's see why. Okay, more concretely, what makes it ambiguous based on the definition up there. Okay, all right. So here are two parse trees for a equals b plus c times a. Okay, we don't give the derivations, we just give the parse tree directly, okay, which is fine. You can actually go through a derivation and then construct the parse tree if you want. But if you get lots of practice in this kind of things, you can actually go ahead and draw the parse tree directly, okay. So that's what we've done here. But we were able to draw two different parse trees for the same expression, okay. You can see that in the first one, I'm going to use this small tool here, the circling tool, okay. Yeah, here. And I want to show something here as well, okay. Yeah. So if you look at these two pieces, okay, on the first parse tree, of course, the top part is the same, assign. That's you have to start with assign, right? That's a start symbol. And then there's only one rule for assign, so that has to expand into id equals expression. Same thing here, assign id equals expression. So the top part of the tree is the same in these two, okay? But now it's time to expand. I guess you can expand the id next and then make it a. And same thing here on this side, you want to choose A, not B, otherwise you will not reach a final step, final string. You'll not reach this final string, okay? So it's the same, including the A, okay? So the tree so far is the same. Now we are left with expanding expression, EXPR, okay, on the two trees, okay? So in this tree, on the left tree, we chose to use the second rule, okay, or the first rule for expression with a plus. So we say expression is expression plus expression. Okay, whereas on the other one we decide to say expression is expression times expression. Got it? Why? Because there was a choice there. Okay, there was a choice, exact choice on what to do. Okay, I mean not what to do, but there were two choices, and in one of them we choose one, and the other one we choose the other. Okay, now of course we had to proceed all the way to the end and see whether we get a complete parse tree or not. Okay, but you can see that the two parse trees are now already become different. Okay, even without looking at the rest of the tree, these two trees are different. Why? Because at this point the expression has expanded into expression plus expression, so we have the plus here, whereas on the other side it's times. Okay, and obviously the two trees, maybe the shape wise they may look the same, but the nodes wise, actually even the shape wise they don't look the same, because further down you'll see that there's a small stick here, whereas the stick is to the right, and then this tree is somewhere here. Yeah. So anyway, if you go further, this expression on the first tree expands to id, and then that expands to b. Okay, and then this expression will have to expand to expression times expression. Why? Because there's still a times there, c times a, right? And then this expression here expands to id and then to c, and the last expression here expands to id and then a. Okay, so that would be the full tree for the first option. And then the right side is the second option, where we chose the multiplication first, okay, and then expand it to expression times expression, and this expression expands to expression plus expression, and of course those expands to b and c, and this one expands to a. Okay, so obviously this grammar is ambiguous. Why? We have shown this is how you prove a grammar is ambiguous. Okay, all right. If in case there's a homework problem or a quiz problem or a test problem or something like that, make sure that you come up with a string. Okay, so just one string, and you may have many answers. Just one string is enough. Okay, and for that string, show the two different parse trees. Okay, you don't have to show 10 different parse trees. Just two is enough. Okay, two or more it says. Okay, so in this case we have done that. We have shown a string a equals b plus c times a, and shown two different parse trees for the same string. Okay, and that's why this grammar is ambiguous. Okay, and why is ambiguity a problem? Because the final meaning assigned to this assignment statement may be different, not maybe, will be different in the two, right? Because in the first one we by the way, this is something you should get you should observe in these two trees. Even though we expanded in the first tree, expanded expression using the plus rule first, and then below that we expanded the expression using the times rule. Okay, so we expanded expression first using plus, and then using star or the multiplication in the first tree. Okay, but when we look at the evaluation of assuming that you're going to do the actual calculation, okay, all these trees are evaluated bottom up. Okay, so you can see that since the multiplication is below the plus on the level, okay, you'll see that the C times A will happen first. Okay, and then the result of that will be added to B. Okay, and then the result will be assigned to A. Okay, so in general the rule is as follows: the lower the operator. Okay, this remark is applicable for operators. Okay, the lower the operator in the tree, the earlier it will be executed. Okay, higher in the tree, the later it will be executed, and that's a general property which is true for these operators. Okay, and because times is lower than plus in this first tree, times will happen first, which is actually the correct interpretation, right? Because times has a higher priority over plus, so you want to do the multiplication first. So the first parse tree is really the meaning which the programmer has in mind when they write that expression. Okay, of course without using parentheses. Okay. But the second one is also a plausible order of calculation where the plus happens first and then the multiplication. And what if the compiler chooses the second one to implement? Okay, because it's got two choices, right? This or this, and then that'll be disaster, right? So that's why we don't like ambiguous grammars. Okay, so we will try to avoid them. Not try. I mean, we will avoid them. Okay. All right. So ambiguity, you got an idea here, right? Now, yeah, before we get to the second example for ambiguity, let's dig deeper into this first ambiguity problem and try to fix it. Okay, how do we ensure that the first parse tree, or not necessarily this exact parse tree, but how do we ensure that the multiplication takes place before the plus in such an expression? You see, that's the question. Okay, how do we ensure? Obviously, with this grammar we cannot. Right? This grammar we cannot. We just saw that this is ambiguous. Okay. So the solution is to really modify this grammar in a clever way, have a different grammar in which the multiplication happens first. Okay, and that's this concept is referred to as the operator precedence. Okay, and it is possible to rewrite the grammar rules. Okay, to reflect this operator precedence and avoid the ambiguity. Okay. Got it? So that's not just asking the computer to memorize that, oh, this is like the PEMDAS rule or whatever that rule is. See, I mean, the compiler is not a human being who can memorize, right? I mean, but we have to encode the grammar in such a way that the multiplication gets higher precedence. Okay. All right. So here's the solution. This is a pretty standard solution. So in some sense, you can memorize it or bookmark this page, this slide. Okay, or you can always look up. Okay, this is the pretty standard way to solve this problem. Okay, I mean, you and me are not the first people to try to solve this problem. Okay, this problem was there even the 19th. I mean, obviously, all the time. But seriously, in computer science, this was a problem in the 1960s. People were trying to figure out how to write, or 50s and 60s, or maybe even earlier, you see, because grammars, whenever somebody is dealing with grammars, they probably dealt with this problem, okay, ambiguity and so on. Anyway, the solution is pretty standard, okay. The first rule, no change, okay. That's the assignment rule, and also the last three rules are the same. We don't want to change that. Only the rules for the expression we have to change, right? So you can see what we're doing here, okay. So we are inventing two other non-terminals, okay, one called term and one called factor. Okay, we will see the purpose of this as we examine these rules. Okay, and what we do is we want to allow for whole bunch of, let me go to this this thing here, and let's look at some example here. Yeah, let's look at, I wonder why this went to italics. Okay, let's, yeah, maybe something to do with the times. It doesn't matter italics or not. Okay, this just is some. Let me see if we can fix this here on the next line. Yeah, this I think oh no, it doesn't. Maybe the times is what. Okay, so let's just not a big deal. Okay, so we have this this expression, long expression here. Okay, and you can see that there is a series of pluses to begin with. A plus B plus a whole bunch of pluses. Okay, in the previous example there was only one plus in this one here. Okay, but we have a bunch of pluses. Okay, so and we want and also there's a bunch of times at the end of it. Okay, or it could be in the beginning too, but let's just take at the end. Okay, and so in this case we want the times to execute first. Okay, which means that the times should appear in the tree, parse tree below, lower level, right? Remember we just made that observation, and vice versa. The plus must happen later, right? After the times, so which means the plus should appear higher in the tree. Okay, so that's the observation we use to come up with this new grammar. So look at the rules for the two rules for the plus. Okay, actually there's only one rule for the plus, but the next one, the second rule, transfers control to the times. Okay, got it? So that's how this works. Okay, but there's only one rule for the plus. So what we do is we write a rule. This can be done left recursive or right recursive, and we will see the impact of left and right recursion later on. Okay, so we decided to do left recursion here. We'll say the expression is expression plus term. Okay, and because of this recursion, you would actually get a whole bunch of terms with pluses between them, right? Because if you kept on using the recursive part, that is, you expand this expression with the same rule, this first expression will become expression plus term, and then there'll be a plus term at the end of it, right? And then again, if you did the same thing, you'll have expression plus term, and then you'll have two terms after that. So you'll get a whole bunch of term plus term plus term plus term plus term. Okay. Of course, there'll be one expression still left on the left, but everything else will be plus term plus term plus term like that. And of course, if you want to stop the recursion, you will use this rule. Okay, that's the only rule left. Okay, these are the two rules for expression. So when you do that, you'll get term plus term plus term plus term plus term plus term, a whole bunch of pluses of terms. Okay, and that's the idea here. Using these two rules, you can actually get. So in this case, we'll get term plus term. I'm not putting the angle bracket, the less than greater than sign. Okay. Okay, so we will get the four, these four. Okay, term plus term plus term plus term. Okay, using those two rules. And the reason I did term plus term plus term plus term is because there were there are three pluses, right? 1, A, B, C. Yeah, there's the three pluses and then the four terms of that. Okay, so that's the reason I do that. Okay, and then after this term, the last one, I can expand. By the way, you'll see that very similar rules for term. Now, instead of the expression, we do the term. Term is term times factor. So that's another new non-term that we introduce. And again, with the recursion here, again the left recursion, we can produce a whole bunch of factors. Okay, so this last term, okay, could be replaced. So let me copy this here, just here, and this last term can become a factor. No, it'll be term times factor, right? And again, if you do this 2 times, then you'll get term times factor times factor. Okay, so the times is something. There's some. Got it. Okay, so you can use the next two rules to just on this particular term. Okay, on this term you will do term times factor, and then again term times factor until we get the 3 factors. Okay, let's say we do need 3 factors here. Yeah, a factor here for this, factor for this, a factor this. Okay, yeah. At this point, you would replace this by factor. Okay, So after you use the recursive rules, you'll replace this by factor. So you'll get term plus term plus term plus factor times factor times factor. Okay, so you can see the way we do this is, now the interesting thing is that here it's all in one line, but if you do construct the parse tree, the pluses will appear higher in the tree. Okay, and the times will happen lower in the tree. Okay, because of the order in which we did this. Okay, you should construct a parse tree, and actually we do have a parse tree in the next slide, I think so. Okay, but anyway, we get to this point, and then you'll see that there is actually starting all the way from expression. You can go from expression to term without modifying it, and from term to factor without modifying it. See, and from factor you can go to ID. So there's a direct path from expression to ID via term and factor without introducing the plus and the times. Okay, but you could certainly introduce plus and times, then it won't be a direct path. Okay, so what I'm trying to say is that right now you can actually replace each of these by an ID. Okay, because there is a path, each of these has an ID, and that's how you get this a plus this expression there. Okay, we do get the same expression, but the parse tree, which will be forcefully generated, would prioritize the times over the plus. Got it? And once you get to the factor, because in the original grammar you were allowed to parenthesize it, so that's why you get this parenthesis here. And of course, so this part I don't think we changed. So these are the two rules from the original one where we had expression. You can go back one slide here. You see that expression, these two rules are kept the same, except that now this time they're going from factor, okay? Because we had to go all the way to the factor before we can expand into those, okay? Got it? So this is a very standard trick. So if you got the just idea on how this works, that's good. If you can't memorize it, that's fine. Okay, you can certainly bookmark it and then look at it. But it's pretty standard trick. Okay, so we do it in a 3-level grammar: expression at the top, term in the middle, and factor in the bottom. Okay, expression will take care of the pluses in a recursive manner, and then once we are done with enough of the pluses, then we jump to the term. And then in the term, we take recursively a whole bunches of multiplications. And once we are satisfied with enough multiplications, then we go to the factor. And in the factor, we can go directly to an ID and stop it, or we can go back to the parenthesized expression and then start the whole thing again. Okay, so that's a very standard grammar. So you may want to memorize it or at least bookmark it. Okay, so now let's look at this a equals b plus c times a. Okay, so we start with the assign. Okay, and you will notice that this time. Again, I think I'm doing the leftmost derivation. It doesn't matter left or rightmost, any one is fine. So I'm doing the leftmost. I do the first one, ID assigned replaced by ID equals expression, and this ID becomes an A equals expression. So that until that point is the same as before. Now this expression, you can see that either I can use the pluses or I can go to terms at this point. Okay, and since there are some pluses, at least one plus there, so I want to use these ones at this point. Okay, so that's why I do expression plus term. And because there's only one plus, I will stop the recursive one and then replace the expression by term next. So I go to the next level. Okay, so I get term plus term. Okay, now this term eventually has to become the b. Okay, so that's why I decide to replace the term by factor here and factor by ID and ID by b. Okay, so the next 4 steps are just to transform the term into a b. Okay, then the next term, which is here, will have to account for the c times a, right? So that's why we go with the recursive rule, term times factor for this term, okay, which is the second rule for term, or the first rule for term. And then because there's only one multiplication in this example, I'll change the term to a factor and the factor to an ID and then ID to a c. So I would get the bit, I'll reach this point in the derivation, okay? And then finally this factor here will go to ID and will become an A. Okay, so you can see that there is a very deterministic path which prioritizes the times over the plus in this grammar. Okay, and this is the leftmost derivation. And of course, I have copied the same grammar here, exactly same one here, and I have shown the parse tree for the previous derivation. Okay, and this parse tree actually not coincides with the first of these trees. It does not coincide because the grammar is different. If the grammar is different, it cannot coincide. but it does share the property with that first tree, the left tree there earlier, in that the multiplication is lower than the plus. Okay. The tree looks different, obviously, because there's a term and a factor in this grammar, but in the previous grammar there was no term and factor. Okay, and the plus happens higher in the tree, times happens lower in the tree, which means the times will happen first in the execution of the expression, and then the plus will happen afterwards. And this comment I already mentioned. Okay, it's important to remember. Okay, higher the precedence of the operator, the lower in the parse tree. Okay, or higher the precedence, the earlier in the grammar rules it appears. See? Oh, maybe I should have said later. Okay, there's something not right here. Okay, higher the precedence of the operator, the earlier in the grammar rules appears. No, I think I should say later. Okay, because the precedence later in the grammar. Okay, so the times appears later. So I'll go fix this. Okay, but that's the point here. But you understand, basically, in the grammar, you want to expand using the lower operators first, and then go to the higher operators later in the grammar. Okay, and that's how you will force the higher operators lower in the tree. Okay, yeah, this should be later. Okay, anyway, we'll fix that. Okay, let's go. I guess this thing we have. Yeah, there's one more slide on operator precedence, but there's nothing new here. Okay. Actually, yeah, what is new here is this is the rightmost derivation. That's only same thing, and again the new grammar. This is the rightmost derivation, and actually I would leave it up to you. Actually, it's done nicely here. Please read this step by step and make sure you understand. The red thing means that's what we are replacing. Okay, so assign is replaced by this, and then we choose expression to replace, not the ID. Previously we replaced the ID, but this time it's expression, and it becomes the expression plus term. Okay. And then the term is replaced to term times factors. So the derivation looks a little different than the other one because we start from the right, and you can see that in the right side things are getting filled up with the variables, and this one gets filled up at the end. So you'll actually see towards the right side of the derivations things are getting filled up here, whereas in this one they were getting filled up on the left side. Can you notice that? So that's the normal feature of leftmost versus rightmost. Okay. By the way, this particular parse tree is a unique parse tree for the a equals b plus c times a. Okay, based on this grammar. It's been proven that this grammar is not ambiguous. Yeah, that's it, unambiguous. Okay. Anyway, this is a rightmost derivation here, and now since we have two different derivations, it might come to your mind that maybe I may get two parse trees and then it will become ambiguous. No, that's not true. Okay, if you look at the parse tree for this derivation, the rightmost derivation, it will be the same as the one we saw here. Okay, it will be exactly the same. Only that the order in which these nodes will be created is different. Okay, but once the process is done, the tree is the same. Okay. So those points are summarized here on the left. The connection between parse trees and derivation is very close. Either can be constructed from the other. Okay, and every derivation with an unambiguous grammar has a unique parse tree, although the tree can be represented by different derivations. Okay, like in this example. Okay, for example, here a equals b plus c times a shown to the right is different derivation compared to the one we saw earlier in the leftmost. But since the grammar we are using is unambiguous, the parse tree shown in the previous slide is the same for both these derivations. Okay, you should verify that. Okay. All right. I think that sort of completes this example. Okay. So we started with a grammar which for this assignment statement, which we had seen before, and we observed that it was ambiguous. Okay, and then we fixed it with this trick of going to a 3-level grammar. Okay, and then we looked at left and right derivations for that same string again with the new grammar, and we found that both of them lead to the same parse tree. So the ambiguity is not there. Okay, and also in the process we talked about the precedence of operators. Okay, the multiplication, division, and so on. Okay, the same idea can be carried over to Boolean and to the other type of operators. Okay. All right. The next example is that of associativity, and because we are reaching 35 minutes, I'm going to stop here and come back on the next video. Okay. See you soon.